This picture went viral a few years ago for obvious reasons. Like, come on, look at this thing. It's a very simple double cube, and we focus on those 6 lines. They magically happen to create this nice sequence of roots, from 1 to 6. Root 1 is just an edge of a cube. Root 2 is the diagonal of a face, root 3 is the diagonal of the whole cube, and so on. It's great and all, but mathematicians tend to be greedy. Maybe we could extend this sequence and do better than that? Let's add another cube. Okay, we have square root of 9, 10, 11, but it leaves a gap, and gaps are not good. We are still missing 7 and 8. Well, maybe we could add a cube to its bottom? Okay, that's progress. We've got square root of 8, but where is square root of 7? Sure, we could keep piling on those cubes and it would keep producing new lengths, but no matter how many we add, square root of 7 is never going to show up. And the general reason for square root of 7 and for a whole lot of other numbers too isn't some quick observation. It's one of those long-running puzzles in mathematics. This exact question, how many numbers can be found in such cubic solids, kept mathematicians awake at night for over 2000 years. And it gave rise to the field now known as additive number theory. So let's jump into this rabbit hole and find out what math is hiding behind this double cube. Take another look at the viral double cube. Let's start by proving that square root of 7 really can't be the length of a segment sitting inside this or any other solid built out of unit cubes. But what does that even mean? Which segments are we even talking about here? Look at those 6 lines. Each one starts and ends at a vertex of one of the cubes, and that's exactly the property we want. This segment here doesn't count because it lands on an edge instead of a vertex. A much better way to look at this is to drop the double cube into a 3D coordinate system. The key observation is that the vertices of the unit cubes are exactly the points with integer coordinates. It allows us to drop the cubes entirely and restate the problem. Can you find 2 points in 3D space with integer coordinates whose distance is exactly square root of 7? So take 2 such points, lattice points as they are called, with general integer coordinates k and m and abc. The distance between them comes from this formula related to Pythagorean theorem. If that were to be equal to square root of 7, the expression under the square root would have to be equal to 7 itself. And since all of those differences are integers, we can rename them and simply write 7 is equal to x squared plus y squared plus z squared. So even though this problem is geometric by nature, the solution is going to come from algebra. To rule out square root of 7 as a distance between 2 lattice points, all we need is to prove that 7 cannot be written as a sum of 3 integer squares. And that part turns out to be surprisingly easy. The fastest route is to look at which squares are even available to us. The first 3 are 0, 1 and 4. All are fine. But now take a look at 3 squared. That's 9, already bigger than 7, so it's useless to us. And every square after that is bigger, so the only squares we can use are 0, 1 and 4. Now we want to pick 3 of those numbers, with possible repeats, that add up to 7. Can we? First of all, we have to use at least one 4, because zeros and ones alone give us the maximum of 3. But we can't use 2 of them either, because 2 4s already give us 8, which overshoots. So it must be exactly 1 4. And then the best we can do is 4 plus 1 plus 1, which is 6. Not enough. Therefore 7 cannot be written as a sum of 3 perfect squares. So just to recap, we proved that square root of 7 cannot be found in such cubic-like shape, which means that we cannot do better than that. Now we could call it a day, but as a fellow mathematician, I want more. 7 is not a sum of 3 squares, but numbers 1 through 6 are. So a natural question occurs: which numbers can be split into 3 squares and which ones can't? What do those numbers look like? Is there a pattern, or is it messy like with primes? In fact, this question has a neat short answer, and it is so hard to prove that it absorbed the minds of the greatest mathematicians: Euler, Gauss, Legendre or Diophantos. To fully understand this story, we need to go way back to ancient times. The Pythagoreans placed great importance on number theory, in particular on parts related to geometry. This led to their interest in triangular, square and more generally polygonal numbers which come from geometric constructions. For example, we can build a triangle with side 2 out of just 3 dots. Side 3 takes 6 dots, since we add a new row of 3 to the previous triangle. And so on. That's why the second triangular number is 3, the third is 6 and the fourth is 10. We also define the first one to be 1 and the 0th one to be 0. This lines up with our intuition. Side 1 means a single dot. Yep, this single dot is a triangle, and you won't convince me otherwise. And, well, triangle with side 0 is simply no dots, because there's no triangle. In similar fashion you can define square numbers, pentagonal numbers and so on. Oh, and the square case is genuinely interesting, because those are exactly the perfect squares: 1, 4, 9, 16 and so on. The Pythagoreans really were onto something here. They, and many other mathematicians over the years, discovered, or maybe invented, a lot of identities tying polygonal numbers together. For example, that the sum of 2 consecutive triangular numbers is a square number. Or that 8 times any triangular number plus 1 is a square number as well. Then, much later, in the 17th century to be precise, Claude Gaspard Bachet, who was also into the topic, took a different approach to those numbers and proposed what we now call Bachet's conjecture. It says that every natural number can be written as a sum of at most 4 squares. And that's the turning point of our story. Let's focus on the number 4 here. Is it optimal? Maybe 3 squares are enough. Well, we've seen already that some numbers can't be represented as a sum of 3 squares, the 7 for instance. But are there more? In fact, Diophantos proved that there are infinitely many of those, and he did it without even trying to. In his magnus opum, EYPHKA, Diophantos solved a whole bunch of self-posed problems, but I want to focus on this particular one, problem 11 from book 5. In this problem we want to split the number 1 into 3 parts, such that each of them, after adding a given number a, becomes a rational square. Add those 3 squares together and you get an equivalent formulation of this problem. We want 3 rational squares, each greater than a, adding up to 3a plus 1. Nice, that kinda looks like our problem. And Diophantos, while solving his, solved a part of ours too. You see, he stated that the number a here cannot be of the form a to b plus 2. Since integer squares sit under the umbrella of rational squares, his result also tells us something about which numbers can't be written as a sum of 3 perfect squares. Plugging this a to b plus 2 into 3a plus 1, we get that numbers of the form 24b plus 7 are not representable as 3 squares. And that really is true, which we are going to prove right now. To do that, we need one simple tool, modular arithmetic. It might sound fancy, but it's really just another way of writing division with remainder, where you only care about the remainder itself. Imagine dividing a number n by 8. You write that n is equal to 8b plus remainder r. In modular arithmetic, we would say that n is congruent to r modulo 8. As simple as that. Now, our numbers 24b plus 7 are of the form 8 times 3b plus 7, so all of them leave a remainder of 7 when divided by 8. In other words, 24b plus 7 is congruent to 7 modulo 8. For us, this means that if such a number were a sum of 3 squares, that sum would also have to be congruent to 7 modulo 8. And here's the fun part. Remember our proof that 7 cannot be written as a sum of 3 squares? Almost the same line of reasoning does the job here as well. The key is to notice that a perfect square can be congruent to only 0, 1 or 4 modulo 8. Take any square, call it x squared. Divide x by 8 with remainder, so that x squared becomes 8y plus r squared. Expand it and group everything that's divisible by 8. Those grouped terms vanish under modulo 8, which leaves x squared congruent to just r squared. Nice. Now we only have to check the different remainders x can leave when divided by 8, and there are only 8 of them, the integers from 0 to 7. Running through all of them, modulo 8 gives exactly what I promise. 3 options and that's it. Every perfect square, no matter how big, leaves a remainder of 0, 1 or 4 when divided by 8. Now take any 3 squares and add them up. The remainder of the sum depends only on the remainders of the parts, and each of those is 0, 1 or 4. So all we have to check is whether you can build a 7 modulo 8 out of them. The biggest sum possible here is 4 plus 4 plus 4, which is 12. While the next number leaving a remainder of 7 is 15, way out of reach. So the only way to get a remainder of 7 is to hit the number 7 exactly. But that's precisely what we ruled out earlier. Which means a sum of 3 squares simply cannot leave a remainder of 7 when divided by 8, while every number of the form 24b plus 7 does. Therefore we arrive at a contradiction. Diophantos was indeed right. This proof actually shows something more. Notice that we never used the 3 hiding inside that 24. So the number 24 in Diophantos' result can be replaced by 8 and everything still works. Therefore, no number of the form 8b plus 7 is a sum of 3 squares. This is something that Descartes noticed many years after Diophantos' results were published. And Bachet, yes, the same one as in Bachet's conjecture, spotted that even the Descartes condition wasn't enough, since numbers of the form 32b plus 28 also can't be represented as 3 squares. But even both families don't give us the whole picture here. There are far more natural numbers that can't be represented as a sum of 3 squares. And the first person to notice this was Fermat. Pierre de Fermat was one of those mathematicians that touched a lot of subjects and stated a lot of conjectures, some of which you may know very well, like Fermat's last theorem. And the 3 squares problem was no exception. Fermat shows here too. But, unusually for him, he contributed quite massively. Fermat noticed something brilliant. The two families we just met, Descartes' 8b plus 7 and Bachet's 32b plus 28, are secretly interconnected. The second one is just the first one multiplied by 4, and Fermat claimed we can multiply not only by 4, but by any power of 4, and the property still holds. This essentially follows from this one very simple statement. If 4n splits into 3 squares, then so does n. To prove it, we will use the same modular arithmetic tricks as before, only with 4 instead of 8. An even number squared is 4r squared, so it leaves a remainder of 0 when dividing by 4. An odd number squared is 4 times r squared plus r plus 1, so it leaves a remainder of 1. And these are the only options, which means that this time the remainder depends only on the parity of squared number. So suppose 4n can be split into 3 squares, x squared plus y squared plus z squared. The left side is divisible by 4, so the 3 remainders on the right have to add up to something divisible by 4. And out of zeros and ones, the only way to do so is by choosing 3 zeros. which means that all three squares are even, and we can write them as 2a squared plus 2b squared plus 2c squared. Then divide everything by 4, and that's it. Here's the representation for n. Implication works in the way that we can just read it backwards, but we need to negate everything. So if n can't be written as a sum of three squares, then 4n can't either. And it means that neither can 16n or 64n all the way up. And since numbers 8b plus 7 can't be represented as a sum of three squares, neither can numbers of the form 4 to the power of a times 8b plus 7. Fermat, with this simple observation, generalized those two results into a whole family of numbers that cannot be written as a sum of three squares. And he claimed that these are the only ones. The problem is, Fermat is Fermat. He liked to make empty promises. And yes, you've guessed it, he didn't prove it entirely, only the part we already covered, which is that those numbers can't be represented as a sum of three squares. Fermat never found out why every other number, not of this form, is representable as a sum of three squares. And honestly, this doesn't surprise me at all. Not because Fermat liked to complain about margins being too small, but because even the hardest proof of this theorem is still brutally hard to comprehend. And the original one, from the 18th century, absorbed the mind of about every great mathematician of the era. This conjecture, stated by Fermat in 1636, gathered the finest mathematicians of the 17th and 18th centuries. Descartes and Lagrange worked on it, ticking off smaller cases. And so did Euler, who honestly did a ton of work on this topic. For instance, he found a connection between the 8m plus 3 case and triangular numbers, which he couldn't quite use. In fact, Gauss picked it up 66 years later in a theorem now called EYPHKA theorem. Euler also corresponded with Lagrange and Goldbach, and together they got really close to the final proof. But the one who crossed the line was Legendre, who with some ridiculous brute force method finally proved the whole thing in 1798. That's why we now call it Legendre's three-square theorem. This result is a culmination of over 2000 years of hard work, done by hundreds, if not thousands, of great mathematicians. It's a beautiful story, but a bittersweet one. Bitter because modular arithmetic is nowhere near enough to finish the job. Everything we've done so far can only ever rule numbers out, not create a representation. Sweet because the refined proof, the one that mathematicians reach for today, published by Diophantos in 1850, pulls out some absolutely exquisite machinery. The first ingredient is the theorem that has famously been proved in over 240 different ways, the law of quadratic reciprocity. The second thing Diophantos needed was his own theorem on arithmetic progressions, which says that if a and b share no common factor, then the sequence an plus b contains infinitely many primes. And the third and last ingredient were ternary quadratic forms, plus the entire theory built around them. Every single one of those is hard to prove on its own. This is the cost of proving Legendre's three-square theorem. So no, sadly I cannot show you the whole proof today, because that would make this video like 3 hours long. But that doesn't mean it's over. Surprisingly, Legendre's three-square theorem is not the last chapter of this story. Fermat polygonal number theorem is. For context, we'll need to go back to Bachet, who, as I've said earlier, conjectured that every number can be written as a sum of at most 4 squares. But there was one detail I deliberately left out. Fermat jumped on this result and stated a much more general conjecture. And I quote, "I was the first to discover the very beautiful and entirely general theorem that every number is a sum of at most 3 triangular numbers, every number is a sum of at most 4 squares, every number is a sum of at most 5 pentagonal numbers, and so on ad infinitum, whether it is a question of hexagonal, heptagonal, or any polygonal numbers. Oh, and here's the fun part. I cannot give you the proof here, which depends upon numerous and abstruse mysteries of numbers, for I intend to devote an entire book to this subject. Spoiler, he never did. And other mathematicians had to finish job for him. We'll start from the end. The pentagonal and higher cases were handled by our Lord and Savior Cauchy in 1813. The 4 squares case was done by Lagrange in 1770. But the 3 triangular numbers case is something I want us to prove. We are in for a treat. Just to make sure we're on the same page. We want to prove that every natural number can be written as a sum of 3 triangular numbers. We defined those back at the start of this video, but I never gave you the algebraic definition. The nth triangular number is the number of dots in a triangle with side n, which is just 1 plus 2 plus 3 and so on up to that final row of n dots. As per anecdote from Gauss's childhood, to find an explicit formula for this sum, one just needs to double it and sum it in reverse order. Now we can see that each column here sums up to n plus 1, and there are exactly n columns like that, so the whole thing adds up to n times n plus 1. And since we calculated 2 such sums, we just need to divide it by 2, and here we go. The algebraic definition of the nth triangular number is n times n plus 1 divided by 2. The first person to actually prove that every number can be written as a sum of 3 triangular numbers was actually Gauss himself, because who else? And we are going to follow his line of reasoning. It comes down to showing that representing a number with 3 triangular numbers is equivalent to something we already know. Let's write n as a sum of 3 triangular numbers, using our fresh algebraic definition. Now we do something rather unintuitive, so you gotta trust me. We multiply both sides by 8, and then add 3 to both sides. On the left is a plain 3, but on the right we split that 3 into ones and hand 1 to each of those parts. And here comes the eureka moment Gauss had while writing this proof. Those 3 expressions are perfect squares, so it connects to Legendre's 3-square theorem. And the best part is, this works in reverse too. Do you remember that a square can only leave a remainder of 0 or 1 modulo 4? Well, 8n plus 3 leaves a remainder of 3, and the only way to build a 3 out of zeros and ones is by getting 1 plus 1 plus 1. So in every single representation of 8n plus 3 as a sum of 3 squares, all 3 squares are odd. Which means that we can always write them as 2x plus 1 squared, 2y plus 1 squared, and 2z plus 1 squared, and run this whole computation backwards. Therefore, a natural number n is a sum of 3 triangular numbers if and only if the number 8n plus 3 can be written as a sum of 3 perfect squares. And that means we are actually done. Legendre's 3-square theorem tells us that the only numbers missing such a representation are those of the form 4 to the power of a times 8b plus 7, and 8n plus 3 is never one of them. So 8n plus 3 always splits into 3 squares, and n always splits into 3 triangular numbers. That's the Eureka theorem done. And with it, the theorem this whole story was building to, the Fermat polygonal number theorem, is finally complete. And that's where our journey really ends. Or does it? We've mainly talked about 3 squares case, but what about 2 squares or 4 squares? How do you tackle those? Also, representing integers as sums of polygonal numbers is a classic problem of additive number theory, a standalone field of mathematics full of magnificent results. Even my own future is tangled up in it, because in October I'm starting a PhD on topic that has me using Legendre's 3-square theorem all the time. case in point that this subject and this journey is far, far from over. Who would have thought that this silly picture hides so much mathematics?